So now we've dealt with reasonably well how a capacitor works and how it acts in a circuit. Now, when you have a real circuit, and I just hauled a graphic card out of a computer, well, John got it for me. If you look at this, all of these little round guys, they're all capacitors. This is what really happens. You don't ever have a capacitor in a circuit. You have lots of capacitors in a circuit. So that begs a good question. How do you hook them all up, and how do you deal with them when they're all hooked up? There are two ways to connect circuit elements when they're in a circuit. You can connect them in series or in parallel. We're going to deal with in series first. And when we say in series, a way to think about that is that they're all in a line. So your wire comes out of your battery, goes into one side of your capacitor, then you get another wire out of that capacitor, that wire goes into the next one, then you connect a wire straight from a second capacitor to the third, and you go from the third right back to the battery. Everything is all in a row, so one after the other. That's what a series capacitor is. So what happens in a circuit like this, if you've all connected them in a line, as soon as you hook up this battery, the charge starts to flow. So positive charge comes out of that positive end of the battery. So our little pluses come out and they start to move. They go along the wire, so these are our plus charges, and they come down until they hit the first top plate of that capacitor. As soon as it hits the top plate of this capacitor, charge plus Q piles up on this plate, but it can't go anywhere because it's stuck. There's a plate, there's nowhere to go. But what can happen is it can repel an amount of charge, negative Q, from here. Or it can repel an equal amount of positive charge. I'm sorry, I tangled that up when I said it. So every plus charge here repels a plus charge here. So those pluses come down to here. They land on this plate. Since all the pluses have left this plate, this one now overall is negative. Okay, then that happens again. The pluses leave this one and go down to this guy. Then this one is left negative. And then the pluses leave this plate. They get going. And they come back around the circuit. So that's what happens with the charge in the circuit. So we connect the battery, or source of potential if you prefer to say it that way. Once you connect it, the charge flows. And what that means is that every capacitor has the same charges on the plate. So one plate is plus Q and the other plate is minus Q. So that's the deal when you have capacitors in series. All of those capacitor plates have the same charge. So maybe that's even worth putting in a circle. So this is our distinctive feature about capacitors in series. They all have the same charge. So let's see what else we can think about this. Now we have three capacitors. They each have a charge, so there's going to be a potential difference across each plate. So the battery supplies some potential difference. That potential will be split over the three plates. So let's see what that looks like. So if our top capacitor has charge C1, it has potential delta V1. Our second capacitor has capacitance C2. It has charge delta V2. And our third capacitor has capacitance C3 and potential delta V3. We can write down what each of those potentials are. So we know that C is Q over delta V, so delta V is Q over C. Okay, let's put these two ideas together. The potential is split over the three capacitors. So our total potential supplied by our battery, sometimes we're going to call it epsilon, sometimes you might call it delta V, doesn't really matter which. This potential is going to be these three guys added up. So that's another relationship that we have. Delta V is delta V1 plus delta V2 plus delta V3. So then this is equal to delta V1 is Q over C1 plus Q over C2 plus Q over C3. So this is a way to write down our total potential. Okay, well, let's think about this for a second. Something we could do is we could create an equivalent circuit. What an equivalent circuit means is that we could pop out these three capacitors, we could put in a new single capacitor, and that new single capacitor would have the same amount of charge as these three together, and it would have the same potential. Okay, so an equivalent capacitance is if we take these three out, we put a single one in, but we still get the same charge. So that's what an equivalent circuit is. So if we take out these three and we plug one in, then we replace it by an equivalent capacitor. And what we know is that our equivalent capacitor is going to have the same total charge and the same total potential. Okay, why don't we make a note there about what we mean by equivalent circuit. So we replace C1, C2, and C3 by a single capacitor that we say has capacitance C with an EQ on it, EQ for equivalent, and that equivalent capacitor carries charge Q and has potential delta V across the plates. Potential delta V. So C equivalent is Q times delta V. I've got a delta V over here. I'd like to pull this into it. So that tells me that delta V is equal to Q over C equivalent. Okay, I'm going to put this in right here. I'm going to set it equal to this, and let's see what we get. Okay, you probably notice that we have a Q in every single term, so we can divide both sides by Q. And we end up with the result that says 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. So this is how we find equivalent capacitors when they're connected in series. Shorthand, you might say this is how you add capacitors in series. So this is equivalent capacitance for capacitors in series. Okay, I didn't have much room, so I wrote a little bit of shorthand. Equivalent capacitance for capacitors in series. This is a pretty important one, and you should definitely stick this on your sheet of notes. I'll have a try this at home. What would you get for an equivalent capacitance if each of these three capacitors had a capacitance of 1 picofarad? I'll leave you to try that one, and I'll start to work on a different example for us to go through. So that straightforward one will be for you to try at home. This slightly more detailed one we'll do together. So for this one, I still have 3 capacitors. The capacitances are 12 microfarads, 4 microfarads, and 6 microfarads. I probably suggest that you just hit pause and try this on your own first to see if you get the same answers as I do. So a very quick recap, if we have capacitors in series, what we know is that they all have the same charge. And the potential gets divided. Okay, so what we can do is let's take our circuit and let's draw an equivalent circuit. So I've got my battery. Rather than draw out the battery, I'm going to do the circuit diagram element for the battery. And I'm taking out 3 capacitors and I'm putting in one single capacitor that has a capacitance called C equivalent. So I'm trying to find the charge on every capacitor and I'm trying to find the potential across every capacitor. The first thing I'm going to do is find my C equivalent. So my potential on my battery I'm going to call delta V. And I'll remember to find equivalent capacitances I have to do that reciprocals thing. So I know that 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Fill in my values. 1 over 12 plus 1 over 4 plus 1 over 6. You can fill in units here. I think I won't just because I don't want it to get too cluttery. At this point you could go straight to your calculator and find numbers with decimals. I'm a fractions kind of person, so I'm going to go with fractions. So I've got 1 over 12 plus 3 over 12 plus 2 over 12 to give me 6 over 12. So 1 over C equivalent is 6 over 12. My C equivalent then is 12 over 6, or 2 microfarads. Okay, now I know my equivalent capacitance in this circuit. I know my potential is 30 volts, so I can find my charge. I remember that C equivalent is equal to the net charge on that equivalent capacitor divided by the potential across the plates. So my Q is equal to C equivalent times delta V. So 2 times 10 to the minus 6 farads times 30 volts to get a charge of 6 times 10 to the minus 5 coulombs. This charge that we have on this plate, the equivalent, is the same as the charge on each of those 3. So I'm going to say that that's C1, Q1, Q2, and Q3. So these 3 capacitors have the same charge as each other and the same charge as on the equivalent capacitor. What's the potential across each capacitor? Well, C is Q over delta V. That means delta V is Q over C. So I'll use that expression to find my 3 potentials. Delta V1 is the charge on the capacitor 1 divided by C1. So 6 times 10 to the minus 5 coulombs divided by 12 microfarads to get 5 volts. My potential across my second capacitor, Q over C2, same charge again. This capacitance is 4 microfarads. So I get a potential of 15 volts. And then for my third, I've got Q over C3. So I've got my charge divided by 6 microfarads. And I get a potential of 10 volts. If you wanted to double check your algebra here, and that's always a good idea, you might add up these 3 potentials and make sure they equal 30 volts. So 10, 15, and 5, yep, that equals 30. So that's the result we expected.